ठीक है. Okay, so now we'll start looking at modeling and simulations of electrophoresis. This is a two-part lecture. In the first part, we'll look at how to mathematically model the in general electrophoresis techniques. Okay. And you will see that there is a common mathematical model for all electrophoresis techniques, which describes the motion of ions applied moving under applied electric field. And then what you will see is that various electrophoresis techniques like zone electrophoresis, field amplified sample stacking, ITP are just different initial conditions or different setups of the initial conditions and the boundary conditions, and using the same mathematical model. Okay. So, maybe this part you might not those who are not familiar with differential equations will have some difficulty. Just try to appreciate what are the various features in the mathematical model. In the second part of the lecture, if you have access to internet, we will try to do hands on, so that by working on computer you can make mistakes, try to do something which is not expected and see what are the outcomes, and that way I think what you can do is you can run a virtual experiment on your web browser using a tool that I helped develop, and with that you without even doing experiment you can actually learn various techniques yourself. So, that would be more interesting, but let us just try to understand how those tools have been developed first, and then we will see how we can use them. Okay. So, please bear with me for the first part if you are not familiar with mathematical stuff, but it is essential if we have to describe simulations. So, in the morning lecture I have discussed about zone electrophoresis. Okay, I am just doing a quick recap because we are going to simulate this process in the later part of the lecture. So, in zone electrophoresis, as you recall, we have a uniform background electrolyte concentration, a high relatively high concentration of background electrolyte, and the samples are injected at the inlet and we apply electric field. And when we do so, we see that these ions will get separated and the peaks will get diffused over time, and the separation distance will increase over time. That is what we have seen in the first lecture in the morning today, and how we have implemented in microchip electrophoresis is using this cross chip geometry, that is also we have discussed. But for our simulations, we are not going to simulate the whole cross chip geometry, we are just going to do one dimensional simulation, because that is easier to do. So, we will just look at this kind of a process in one dimension and we can see the simulation. Okay. We can simulate this process. So, the idea of doing these simulations is that in advance, if you actually use the parameters that will be used in the experiment, you can get a sense of what will be the peak heights, what will be the resolution of separation, whether the two peaks are separated or not, and this we can try and to simulate in our experiment. Another thing that we discussed in our previous lectures was field amplified sample stacking. I said that if you have a gradient in the concentration of the background electrolyte, you can stack samples. So, we can try to do simulations of this process as well. So, you will appreciate how starting from a low concentration sample, your concentration can increase if you have differential electromigration velocity. Essentially, in the high conductivity region, the velocity is going to be low. In the low conductivity region, the velocity is going to be high. So, the ions will get accumulated at this interface. So, this is also something we will try to simulate. Then we have discussed about ITP. This is a very complicated process to think about, and to design you have to judiciously choose the electrolytes, because in zone electrophoresis the choice of electrolytes is not so difficult, but here the process is very non-linear in ITP, and the choice of Le ion, Te ion, the counter ion, and depending upon the samples that you have is very challenging, and that is where simulations really help. Okay, so my whole PhD was on ITP and coupling ITP with zone electrophoresis. Actually, I spent a lot of time making these simulation tools, and most of the time, we could really simulate various electrolyte chemistries on computer, and so that when you go to the lab and do, after less amount of trials, you can actually get things working. Otherwise, designing ITP experiment is challenging, and it needs a lot of experience, but if you have simulations, you can gain that experience through simulations rather than spending time and spending resources in the lab, in a wet lab. So, why do we need simulations? You all so these are the things related to ITP that we have seen in the morning, but why do we need simulations? So, as you all appreciate, okay, many of you are not familiar with these things, how to do the experiment in practice, how to do electrophoresis in practice. Some of you might not even have access to the equipment, but you can still optimize the processes, how I can choose the process parameters to get improved sensitivity, improved resolution, and all of that practice you can do on the computer, because the models that we have now, the computer models and the simulation tools, they are fairly good representative of the reality. So, I will show you the experiments that we have done and the simulations that we do, they are in pretty good agreement. So, all you can do is you can use simulation tools and make an optimal process, and then you start doing the experiments. Okay, and one of the challenge you will see is in designing Le and Te for ITP. Okay. Another thing is that we can also work on developing new electrophoresis processes, very complicated electrophoresis processes like bidirectional ITP. So, I worked on this for some time, where you have some ITP fronts, anionic ITP fronts moving in one direction, cationic ITP fronts moving in other direction, all together in a single channel. That is very hard to think of, but you can do simulations and then make sense of it. Okay. Another point is that, see, when you do an experiment in a microfluidic device, okay, while doing the experiment, you can measure only the things that your detector gives you. You might get a fluorescence signal, you might get conductivity signal, but simulations will also give you the spatial and temporal variation of various parameters, like what was the pH at what location, what is the conductivity, how does the conductivity vary with the distance, all these things which you cannot measure using experiments, you can simulate. Okay. So, that is the benefit, and of course, teaching. Okay. I have tried to show you already some simulations in the previous lectures, and they actually help us understand how spatiotemporal variations in properties like conductivity, concentration, pH take place in electrophoresis processes. Okay. So, now we are going to develop the model for simulating electrophoresis. Okay. Some of you might find it a bit challenging, but let us just look at overall processes that go into overall like mathematical terms that go into the modeling, because really we have to solve differential equations to be able to model these processes. So, what we will do is we will start with a simpler version first. We assume that the ions that I have in the solution are fully ionized. There is no association dissociation reactions. So, you have strong acids and you have strong bases. So, you might have, let us say, sodium chloride, potassium chloride, okay, calcium chloride, magnesium chloride, magnesium ions. All of these are, you can consider them to be fully ionized. So, you do not have sodium in non-ionized state, it is mostly in ionized state. You do not have chloride in aqueous solution in non-ionized state, it is not in HCl form, it is in Cl negative form. So, that is what we assume. because if we assume this, then we can assume that the electrophoretic mobilities are constants. Okay. So, let us see. So, what we do is essentially the governing equations that we are going to solve are equations for mass balance. Okay. These are just conservation equations for mass balance. Okay. That is how we describe. So, the equations go like this. Okay. If you consider a small control volume, a small space in your liquid, okay, small virtual region in the liquid. Okay. Think like, you know, maybe you are more accustomed to some reactors and all. So, imagine that I consider tiny volume of liquid, okay, in the microchannel. The rate of change of concentration of some species within that tiny volume will depend upon what is coming in and what is going out. Okay. So, how can ions get in and how can ions get out? What are the various physical processes by which ions can get into this volume and get out of the volume? Okay. What are the processes? One is that liquid will flow. Okay. The ion is carried by the flow of the bulk liquid. Okay. That is called convection. So, it is velocity of the fluid times the concentration. Okay. That is the mass flux that is coming in. Okay. Then you have electromigration. Okay. Let us say there is no flow of liquid, but the ions themselves are moving under the effect of electric field. So, with what speed are they coming? Mobility times electric field, and how much amount of ions, how many, what is the mass flux of ions per unit cross section? Okay. That is mobility times electric field is the velocity times the concentration. Okay. This is the amount of ions that are being that are crossing a particular cross sectional area. Okay. And then what we have is diffusion. Okay. Because of diffusion also you will have flux in and out of the system, and diffusion, the flux due to diffusion is modeled as minus diffusivity times the gradient in concentration. So, why is this minus sign in diffusion? Minus sign is because mass will flow from high concentration to low concentration, and there is this derivative term. So, you put all of this together, you get a transport equation. This is a partial differential equation. Okay. And we need to solve this equation for all the ions that I have in the system. Okay. So, I may have an electrophoretic system which has 10 different species of ions, maybe sodium, calcium, chloride, sulphate, magnesium, so many ions. So, each of these species will be described by a different differential equation, because those species will have different mobility and different diffusivity. Okay. Now, we also have one more parameter over here, one more variable over here, that is the electric field. Okay. So, electric field also depends upon, what does electric field depend upon? I have a capillary, I am applying voltage. What will electric field depend upon? It will depend upon voltage. It will depend upon the voltage, it will depend upon the length, but it is also going to depend upon what is inside the capillary. Okay. Is the solution more conductive? Is it less conductive? Okay. Because if the conductivity is uniform, then electric field is just voltage divided by length. But imagine that one part has higher conductivity, other part has lower conductivity. It is like in high school physics. Okay, there is one resistor connecting between this region and this region, and there is another resistor connecting between this region. So, you can have different electric fields in different parts of the channel. Okay. So, the equation for electric field actually can be derived using the electroneutrality assumption. The electroneutrality assumption means at every location in the capillary you have same number of positive ions as same number of negative ions, or you can say the net charge should be 0. Okay. Because you can't say same number of positive and negative ions, because some ions carry more charge, some ions carry less charge depending upon the valency. Okay. So, but the net charge should be the same. So, based on that you can actually derive the Ohm's law. This is the Ohm's law, which says electric field is equal to the current density divided by the local conductivity of the solution. Okay. So, when I say local conductivity, the conductivity is itself a function of concentration. So, conductivity depends upon the concentration of the solution, and here we also have a contribution due to diffusion. Okay. Different ions diffuse at different rates, so they can also produce a current, okay, a diffusion current, but this term is not so important as much as this conduction current. Okay. So, this is my mathematical model, okay, for fully ionized species, but the species that we are going to look at, the chemical species that we will be working with, are weak acids. They are not fully ionized species. So, what we have to see is that we have to ensure that that the dependence of the mobility on the ionization of the species is taken into account. That means, depending upon the pH of the solution, how much fraction of particular species is in ionized state and how much is it in non-ionized state, it will dictate whether the mobility is high or low. Okay. So, for example, what we can do is, typically let us say we have a mixture of sodium hydroxide, acetic acid and phosphoric acid, okay, and we want to simulate this kind of a mixture. So, what are the various acid base equilibrium reactions going on? So, there are a lot of reactions that are going on, and you know that, and in chemistry we know that I give you a particular composition, you mix it, you can always calculate the pH, isn't it? Okay. You can always make buffers, you know how to calculate the pH of the buffers. The same thing we have to do. So, we assume that the acid base equilibrium reactions, they occur instantaneously, they occur at much faster time scales than the time scale at which ions move. So, ions move relatively slow compared to the rate at which acid base equilibrium is established. So, we always assume that equilibrium is already there, always locally chemical equilibrium is already established, acid base equilibrium is already established. So, using this, okay, the mathematics of acid base equilibrium reactions, we can actually calculate what is the pH of the solution. Once we have the pH of the solution, we know that we can actually work out what is the ionization fraction of various species. Okay. So, let us see. Okay. So, it is just generalization of what you already know for acid base equilibrium. Okay. Do you know, right, if you mix acid and base, you can predict the pH. Huh? Which equation is that? What do you name? Hasselbalch. Okay. So, essentially this is just generalization of that Hasselbalch for n number of species. Okay. That is all. Okay. That's it's just you know, mathematical representation of what you do, okay, for simple buffers. Only thing here is that we have n number of species, because in a capillary, in a microchannel at a particular location, okay, in my simulation I may have hundreds of species. Okay. So, we use a model to predict that if you have so many acids and bases, okay, what is the pH. Okay. And once you get the pH, you can tell what is, let us say in this case acetic acid, what is the fraction of acetic acid in ionized state, what is the fraction in non-ionized state. Okay. Now, in this example, we have two types of species. One on the top, sodium and acetic acid are univalent species. They can dissociate into, okay, they have only one ionization state, okay, or dissociation state. But here I have, what is this? Phosphoric acid. It has 3 ionization states. Okay. So, what we actually solve for is the total concentrations. We solve for the total concentration, that is, the total concentration means concentration of a particular species in ionized state plus non-ionized state. So, for one species family we write one equation, okay. And if we do so and we work out the math for this, so essentially by solving these set of equations, the output is the pH of the solution, the local pH of the solution. The pH of the solution in capillary electrophoresis is going to change with location and with time. So, at every time and at every location you have to calculate the pH, okay. And once you calculate the pH, you will have to calculate the fraction, okay. Let us say this is the ionization fraction of species X in Z ionization state. For example, phosphoric acid in -2 ionization state, this formula can give you. Okay. So, this we have to solve at every time, okay, every time step at every location. Now, we can generalize our mathematical model. Okay. We have similar equations like we have for for fully ionized species. The only difference now is that if you look at this equation, this has this advection term due to motion of the bulk fluid. This is the electromigration term due to the motion of ions under the effect of electric field. This is the diffusion term because of diffusion. The only difference between fully ionized species and weakly ionized species is that this mobility is not a constant. This mobility is a function of pH. Okay. Essentially, let us say for univalent acid, okay, this mobility is the mobility of the anion multiplied by what fraction of the acid is in the anionic state, okay, and which is given by this term. Okay. But you see the non-linearity over here. Okay. It is highly non-linear problem because of two reasons. So, for at any location you have some concentration of various species. Okay. Those concentration of species will dictate the local conductivity of the solution. The local conductivity will dictate the electric field. Okay. The electric field will govern the speed of the ions, okay, and the speed of the ions is going to change the concentration. That is one complication. Another complication is the local composition of the ions is going to change the pH. The pH is going to change the mobility is going to change the concentration. Okay. So, that is why doing nonlinear electrophoresis in presence with weak electrolytes, okay, is a highly nonlinear problem. So, sometimes it is very difficult to predict what is going to happen in the simulation. Okay. Only through experience and running simulations you will be able to understand why pH is increasing in a particular location, why electric field is increasing in another location. So, what we do is that we solve these equations. Okay. We can also derive approximate equations for channels with variable cross sectional area if we work with average concentrations, concentrations that are averaged over one cross sectional area. But for this lecture we will just assume that the channels are straight. Okay. These are straight channels. Let us say we say there is no variation in the cross section and therefore, these equations will apply for single dimensions. Okay. So, we will just assume area is constant. Okay. We will not do variable area. So, the equations will simplify to this. Okay. One dimensional, we have one dimensional problem. Okay. So, concentrations are functions of the spatial location x and time. Okay. So, they can vary in space, they can vary in time. Okay. And these coupled equations we have to solve together. Okay. So, depending upon the composition of the electrolytes, sometimes you may have just 3 species in electrolyte, sometimes you have 20 species. For other electrophoretic processes, there is one process called isoelectric focusing, which is used for protein purification. Okay. You may have 300, 400, thousands of species, because it has some species called ampholites. So, there you have to solve thousands of equations together, and all of those equations are coupled with each other, because each concentration contributes to pH, each concentration of each species contributes to the conductivity, okay, and conductivity will dictate the speed of the ion. So, it's a challenging equation, challenging system of equations, and it's not that like you already code, you develop your mathematical or your simulation tool for 2 equations or 10 equations. We have to simulate for general number of equations, okay, because when you tell these are the species that I have in my system, okay, then your numerical solver or your simulator has to work with those many number of equations. So, very quick introduction to, or brief introduction to how we solve this. Okay. So, these are partial differential equations, okay, in space and time. Okay. We need to solve them, but computers cannot handle continuous variables. So, we discretize the domain into finite number of grid points. You can't define concentrations at all the locations, because computer has finite memory. Okay. So, these are called nodes. Okay. I am telling you this because we are going to use this in our simulation exercises. When we simulate this, you will have to choose the number of grid points. So, if you have large number of grid points, okay, intuitively it is clear that you are more closer to the reality. If you have less grid points, you are having a poor approximation of the actual system. The next step is to approximate the derivatives, okay, the spatial derivatives del by del x. How do we approximate the derivatives? We use the approximation formulas, okay, the finite difference formulas for approximation. Okay, because we do not know the see, if I know, let us say f of x is e to power minus x, then you can calculate the derivative, but we do not have analytical expressions. We just have values of these functions at discrete locations, and using those values we need to find the derivatives. Okay. So, there are various schemes. Okay. For an end user, what you need to know is the order of accuracy of scheme. Okay. So, typically there is one scheme called upwind scheme or first order scheme, which is presented over there. So, first order schemes are okay, will give you stable simulations, but they are inaccurate. Okay. High order simulations will give you, in some cases, unstable simulations if your grid is not fine enough, but they are more accurate. Okay. So, there is nothing like you can get a numerical method which is easy to solve and also accurate. Okay. There is always a trade off. Okay. So, there are various schemes. Okay. This scheme that I have presented is called finite difference method, finite difference method for approximation of derivatives. Okay. So, in mechanical engineering we work on simulating flows of fluids. Okay. It is called computational fluid dynamics, CFD. In CFD, we study all these methods, how to develop advanced methods for solving, which are more accurate and which are more robust. So, there is another method called finite volume method, but as a user you do not really need to know what this method is, but it's something similar to finite difference method, and you can use this method, and we have used this method to develop our numerical code that I will be showing. Okay. So, that is one thing. Okay. Now, what we do is the spatial derivatives, now we approximate in terms of the function values at various grid points. Okay. So, okay, these derivatives we can make an approximation in terms of the flux values at various grid points. So, what we do is that we end up getting differential equations for concentrations at every grid point. We get coupled ordinary differential equations. Okay. For every concentration of every species at every grid point. So let me give you an example. So if you have a domain of, let's say, this big capillary, you say that I want to approximate this in terms of 100 grid points, okay, and there are 3 species. So at every node, every grid point, you will have to solve for concentration of 3 species. So in all, you will have 3 ordinary differential equations at one grid point, and you have 100 grid points. So you have 300 ordinary differential equations. Okay. If you have 100 species, okay, or let's say 20 species and 1000 grid points, you are at every time step from going from, let's say, 1 second to 1 millisecond, okay, you are solving 10 into 20 into 1000 whatever. So you will get 20,000 equations together, okay, which is actually not difficult on modern computers. So we have developed tools, okay, for the end user, which can be implemented even on a web browser, okay. So there are known methods of time integration to solve ordinary differential equations. Those who are familiar will know, but essentially you can numerically solve at discrete time steps. So you can solve for small time intervals these equations, okay. Some tools will allow you to adapt the grid, okay. So the idea is this, okay. So in ITP, you know that we will have very sharp concentration gradient, okay. To resolve a sharp concentration gradient, you need very fine grid spacing. The computational grid, the grid points should be very close by. So if we take very fine grid throughout the domain, then the number of grid points increases, the number of equations will increase. So what we do is that we have algorithms where these grids will move in the direction where you have sharp concentration gradients, where you don't need these grid points, okay, you remove from there and you place them in location where there are concentration gradients. So you can make your simulations more efficient, okay, and the speed can be increased. Okay, so this is just a very brief introduction to what goes on in developing these numerical simulators. Okay, as an end user, you just need to have some idea, like which scheme should I use, which tool should I use, okay, should I trust my simulations, when should I not trust my simulations. That is what you should understand. So fortunately, in electrophoresis community, the good thing is that all of the tools, in fact, most of the simulation tools are available to the public for free, and you can just use them on your personal computer. So here are some simulation tools, okay. So I'll use one of them to demonstrate these simulations. So let's see. So Simule is developed by researchers in Czech Republic, and this was originally the only simulator available, and the new version is really good. It's very robust and it has a large database of chemical species you can use for testing, and the new interface that they have released with the version number 6 is really user friendly. You can use it if you want. All other 3, fortunately, I have been involved in making all the 3 simulators. Okay, they solve similar equations, but they have different utility. So this simulator was developed at Stanford University. I was one of the contributors to this. So this simulator works on MATLAB, and it has in terms of accuracy, it's very accurate. It has you have a choice of choosing the order of accuracy, because in Simule you don't have handle over what is the accuracy of the computational techniques that you use. In this, you can get that, and it has adaptive grid refinement. Simul does not have. So, here you can solve the same problem in lesser amount of time. Okay. So, that is the benefit. Okay. This is another tool that we developed along with the team at Stanford University with Professor Juan Santiago. So, the objective of this tool was not to be very accurate, but even like a beginner can actually quickly use it without installing the software or anything. So, it is available on the web browser. So, in today's lecture, because I find this tool very handy, okay, we can use this tool on our web browser to do the simulations, but one has to be careful about the accuracy, because it uses simpler, easier schemes which may have lower accuracy, but qualitatively you will get the correct answer. Okay. Then we also worked on developing a very high accuracy solver. It is called pseudospectral Python code for electrophoresis. So, pseudospectral method is the highest highest accuracy numerical scheme that you can develop. The need for this program came because many times I will show you. So, for example, you can use this Python code to run thousands of simulations, okay, and you can program it in this fashion. These are based on graphical user interface. So, if you have to do 1000 simulations, it is very difficult. You have to do it manually. So, if you have a Python based code where you can actually make the input files and you can run them in a batch, okay, you can do a large number of simulations very easily. So, in the later second part of this lecture, I will discuss this tool, and we will try to do some simulation, so that you will understand yourself, by making mistakes, what can go wrong in an electrophoresis experiment. But let us just compare these simulators. Okay. So, Simul simulator is good, but its spatial discretization accuracy is only second order. Okay. The order of accuracy describes how well you can describe the derivatives or spatial derivatives using the approximate formulas. Okay. So, second order is good, okay, but sometimes you need very high order accuracy. So, Espresso and Spice gives you the highest accuracy. This Cafes one, the web browser based, has reasonable accuracy, but not as good as all of them, because we have tried to make a scheme which is more robust to make it user friendly, so that you do not see your simulations blowing up. Okay. So, it is a trade off between user convenience and accuracy. Most of these schemes use similar time integration schemes. Espresso and Spice also give option for adaptive grid. So, you can use less number of grid points and simulate a more complicated problem. Espresso, we also integrated variable cross sectional area feature. So, for example, when you have ITP in a variable cross sectional area channel, you can simulate in Espresso, and all of them have graphical user interface, except Spice one, which was not made for graphical user interface. So, what I will show you now is some test cases, and then our objective is to run some of these test cases, set up these test cases ourselves on our computer, and then try to run those, okay, in one of the simulators. So, we will use only Cafes, because you will need MATLAB for this, Python for this. So, it is better that we just use what is available on a web browser, and those who do not have a computer may also try it on mobile phone. You can still, I think you can run on a mobile phone also. Okay, but let us try to do let us just look at the simulations. So, this simulation is for capillary zone electrophoresis. I have quickly shown in the first lecture. So, initially there were two overlapping zones, and they are separating over time. Okay. So, what you see is that these peaks are getting separated over time, Okay. But the background concentration is also changing, because here the concentration of species is, the zones is pretty high, relatively high, that it is changing the local electric field. So, the background concentration is also changing. Okay. If the background concentration was not changing, then you will not get these triangle shaped zones. So, here we have done simulations using various schemes. So, some schemes which are inaccurate but robust will give you this kind of solid line, this black line, okay, where the solution does not capture the peak exactly, it will capture the location of the peak exactly, but the numerical method adds some additional diffusion to stabilize the simulation. Okay. And sometimes if your scheme is not correct, then you will see these oscillations. Okay. So, in the simulator that I am going to teach you, you will never get these oscillations, because we have already artificially added some diffusion to suppress them. Now, let us look at simulation of ITP. We saw this simulation of ITP earlier. Okay. We can try to set up another simulation like this. So, this is leading electrolyte, trailing electrolyte, some sample ions which are separating over time. So, what can you get out of this simulation? What should be the length of the channel, so that my separation is complete? Okay. In what time I will be able to get the separation? These are the things you can simulate before even doing the experiment. And here is the same simulation, just to show that various simulators give you similar answers. So, we verified or benchmarked Espresso and Spice. So, both of them give similar answers. So, you can use any one of them. Okay. Now, for ITP problem, this is a simulation of focusing of two analytes, aniline and pyridine, between sodium and an amino acid. So, here you see that if you choose a less accurate numerical scheme like the upwind scheme, then this interface will not be sharp. Okay. Just because less accurate schemes add more additional diffusion than what it is present in the simulation. Okay. So, you will see more diffused interface, and this diffusion will increase if you have lesser number of grid points. So, this is best learned through practice. So, we will try to experiment ourselves and try to see. Okay. So, the point is that the zone boundary thickness, the thickness of the zone boundary will reduce with the number of grid points. If you use larger and larger number of grid points, your simulation becomes more and more accurate. Okay. But for some schemes, using less number of grid points, you can get that much accuracy. But if you are not worried about accuracy, you are just worried about just qualitatively understanding, then it does not matter. You can use less number of grid points and have an approximate simulation. Okay. So, now at the end of my capillary electrophoresis lecture, I had talked about sample stacking in zone electrophoresis. Okay. So, let me see if I can stop this. Okay. Let us look at this simulation again. So, what I have done is, this is again zone electrophoresis, but I have created a gradient in the concentration of the background electrolyte. So, essentially what you have is, if I can stop or start again. So, you have high concentration background electrolyte, the sample is mixed in low concentration electrolyte. So, when you apply electric field, you see that this concentration initially increases. Okay. The zone becomes narrow, the concentration increases, and then you start seeing these separations. Okay. So, this is how sample stacking and zone electrophoresis can help you increase the sensitivity. So, we can see it again. So, in this plug you have small amount of samples. Now, the concentration is initially increasing, and now once the stacking has taken place, now you get electrophoretic separation. So, even though if you have low initial concentration, you can use this stacking process in the beginning for pre-concentration and then improve your sensitivity. Okay, so these simulators you can also validate, okay, with experiments. So, for example, Espresso we have done validation with experiments. So, let me show you this case, okay, over here. So, this was an ITP experiment where there were 3 species. Okay, we had fluorescein, we had another fluorescent dye called OGCA, and there is another species focused between these two, but it is not fluorescent. So, it is not visible. So, you see the match between experiment and simulation is excellent. Okay. This is experiment and this is simulation. Okay. Similarly, this was another experiment where we did plateau mode ITP with non-focusing tracer. So, we said this, we measured that LE zone was up till here, then we have some analyte focused between LE and TE, and that is what we have simulated. Okay. So, the mobilities besides pH are also function of ionic strength. That is the secondary correction we make in the simulations, and how much sample is accumulated in experiments and simulations, they match pretty well with the simulations. So, the goal is that now that we have validated our simulations, the various people have done lot of experiments, we have tried to validate our tools with those experiments and the match is pretty good. Okay. So, we can trust our simulators and now start building or trying to develop our experiments using simulators. Okay. So, that is about numeric these developing simulators using from first principles using the mathematical tools. This is our recent work, just some idea that we thought about and we tried to implement. So, what we did was that, see, for a person, and this work is specific for ITP only. So, the idea is that for an end user, many times you do not even need to do the full simulation. All you need to know is if this is the LE, this is TE, will ITP work or not? That is all you are interested in. Okay. Or you say this is the sample I want, will this ITP work or not? So, what we did was this. Okay. We used our SPICE simulator, okay, and we did 10,000 simulations for an ionic ITP, 10,000 simulations for cationic ITP. We got a very large database of simulations for a certain type of electrolytes only, univalent electrolytes. Okay. These kind of electrolytes where we varied mobilities between these values, pK between these values. Okay. So, we took a large number of simulations. Okay. Some of them showed ITP, some of them were not consistent with ITP focusing, but what we said was that we take large samples, large number of parameters. We take large samples of parameter values and we do simulations. We got large data set, okay, and it is a highly nonlinear problem. Then what we did was, it is these days very easy to train a neural network model, okay, for classification. So, we said that what are the inputs to my model? Inputs are mobility and pKa. So, I have Le, Te and analyte, each of them has a mobility and each of them has a pKa. So, we feed this, okay, and we train the model based on large number of simulations, and we make only one prediction, whether you get ITP focusing or whether your experiment is going to fail. Okay. And then we trained this model and made a small online tool, okay, it is called ION. All you have to do is, it will not give you spatiotemporal variation of the physical properties. All it will tell you is that if I choose an Le, if I choose a Te, I choose a background counter ion and I choose an analyte and say predict, it will immediately give you an estimate whether your ITP is going to work or not. Okay. So, for an end user, okay, it has an accuracy of 97%. Okay. So, most of the time it is going to work. So, end user sometimes does not even really need to look at the whole simulation, because doing these simulations is also setting up these simulations can also be challenging for some people. So, those who are really into experiments and quickly want to know, okay, let me try this chemistry, you can just put it in this tool. It's a web based tool, and then it will predict, okay, for ITP this is going to work. So, we can try these two tools in the next part of our lecture, where we will do some hands on work. Okay. So, what I will suggest is okay, in the break, okay, I can give you the links to these tools. So, let me see, try to open these links so that we can work on these links in the next lecture. So, is there a way I can share the link with people? Let's see.
Do we have a WhatsApp group yet or not? What? Do we have a WhatsApp group yet?
Yes, we have.
Or you can type this link if you want.
We have a WhatsApp group
You have a WhatsApp group?
of this.
So, I can share it on the WhatsApp group.
Admin has to add me. Huh? Admin.
Who is the admin?
Sir is there. Vikas is admin. Vikas is admin. He's not there today? He's not here today?
You want group?
No sir, group is there. He just want to share the links in the group. For that admin has to add him, na?
Or you can try writing this. Okay.
Group link है.
Wait, I will do something. No, I'll do something. Don't worry. So, let me fix it.
इसको लॉगिन कर देता हूँ व्हाट्सएप अपना यहाँ से ग्रुप में डाल दो यहाँ से
नहीं मैं बता दूँ आसान तरीका बता दूँ मैं कुछ I will give an easier way. Okay, you can scan this code and see if you can open. Huh? No, you will get the link on the phone only. See if it is possible for you to open. At least you will get the link. Okay, this site will take a bit time because it runs on JavaScript. It will take a little time to load. So, if it is, if you
हम तो just WhatsApp खोल रहे हैं, WhatsApp app.
huh? She has WhatsApped you. Select this. ठीक है, it will take time, little bit time to load. Yeah. ठीक है. Another, if you can send another one on WhatsApp. So this is the second one. So these are the two tools we will use. Okay. It will take a bit. Just wait for a bit to load.
This is another one.
This is another one. ये नीचे वाला. So are you able to open the first link? Yeah.
It is opening yet.
फर्स्ट लिंक खुल गया आपका पीछे? जस्ट मे बी
एक ही खोले ना एट अ टाइम, नहीं तो दोनों खोल लेंगे तो फिर एक भी नहीं खुलेगा.
no. Once they are open, there's not much.
We'll have to open both.
Yeah, we can do both.
It's open.
Which one?
Cafe.
Cafes is open. It will take a bit of
Another
time.
one is to be open.
Yeah, that you can open. खुल गया आपका पीछे? Is it open? Okay, maybe mine is initialized with something else. Yours will be empty, so I can remove all of this. Okay. So let's. Should we start with this or?
Could you open?
It's still waiting.
Huh?
I've done it. I've played it.
Okay, fine. Are you ready, guys?
Cafes is open.
Huh?
Cafes is open.
So we can work with the other one first.
Cafes खुल गए
वो खुल जाएगा because the way it is written is that it's not running on a server, it's running on your own computer. So it's when you do these calculations, the calculations happen in the browser only, not you don't need internet after this. Okay. So it will take time to load. But if you have opened the other one, we can. This one is open for you? Yes. Okay, so we can, let's try this one first. This is easier, right? But it's not going to give you much, okay? I mean, you'll just give you one output. So let's see. So, okay. So thing is that let's say we want to simulate. Okay, so this part of the lecture we'll start doing hands-on work. Okay, there are no lecture slides for these in this lecture. So see, this is the neural network based tool that we developed. All you have to do is that you have to give the choice of, it works only for ITP, not for general electrophoresis. You tell whether what LE, TE background analyte you are choosing, and it's going to predict whether ITP focusing will take place or not. That's all. Okay, and it has been trained using large number of simulations. Okay, and the simulations are, some of the simulations are validated with the experiment. So we hope that whatever this is predicting is correct. Okay, so what you have to do to use this simulator is that first you choose what type of ITP are you using. Are you using anionic ITP or cationic ITP? Okay, anionic ITP is to focus and separate anions, negatively charged ions. Cationic is for cationic ITP. Okay. Concentration ratio is the initial composition of the leading electrolyte. So, typically we say that for a well buffered electrolytes, you take let us say ratio of the background counter ion to the leading ion to be 2. Okay. So, we will not change this factor. So, now let us try to design an ITP experiment. So, let us say if you choose anionic ITP, you will be shown only acids over here. Okay. You can also put your own values if you want, but let us say I choose, let us see if it is working. I choose hydrochloric acid. Okay. So, hydrochloric acid will give chloride ion as the leading electrolyte. Okay. Okay. Okay, you can choose hydrochloric acid for example. Okay. Then background electrolyte you can choose, let us say tris. Okay. So, whenever you choose from the database, it will update the mobility and the pK over here.
Here it is already coming next.
Yeah, that is because you are using for the first time. You can just do next and finish it off. It's just help.
Okay.
You can just hit
So cross kar do?
cross kar do. Yeah.
Okay.
Okay. TE and okay. So, see this I have used, you can have a look and then maybe try later. Okay. So, in leading electrolyte I have used the chloride ion, which is an ion of hydrochloric acid. Background I have chosen tris. Okay. Trailing electrolyte I have used heaps. Okay. So, what you see is, first look at this, mobility of heaps is anyway low, but the pK is also high. That means, it is a weak acid, okay, with a low mobility. So, certainly it is slower than the chloride ion, the mobility is lesser than chloride ion. Okay. But I have an analyte MOPS. Okay. So, MOPS has higher mobility in terms of magnitude, and it also actually has it is a slightly stronger acid than heaps. Okay. So, that means, this analyte must focus between this Le and Te. Okay. And from experience I know, okay, and you can also judge. But what you can do is, you can hit predict and it predicts. Okay. It not only predicts, it also gives some number. You can interpret it as a probability, but it is not exactly probability, but it's, you can think that the code is 99% sure that this is going to work. Okay. Because again, this is based on a large data set, limited data set. So, we do not want to give predictions like this is going to work, this is not going to work. Okay. So, there are some cases which are borderline, where the model is confused. It will say that okay, the accuracy, this probability of ITP condition satisfied will be lower. Okay. But here in this case, it is fine. Okay.
Why we have chosen that concentration ratio 2?
Typically, you choose it to 2 because when we, as I said, when you make the electrolytes for ITP, and you want to have certain good buffering, what you do is that you take one part of strong acid and add 2 parts of weak base.
Okay.
So that gives you a good buffering condition. That's all. Yes.
Does it only do the simulations at the pH of the pKa, or is there a way that you can adjust the pH? Heap is
Yeah,
not
yeah.
good
So
for
if you change this,
yeah.
then the pH is not pK, right?
Okay.
Yeah. So you have a handle over here, so you can modify this over here. Yeah. So you can
Okay,
change.
so you that's what you use to titrate your buffer.
Yeah, yeah. So this will help you titrate and control the pH of the LE, and then it will do. But for beginners, we always recommend that you use this ratio to be 2, because then pH is, you know, that pH is equal to the pK. Yeah, that's the only reason. But if you want to do titration, you can change this value. It the model is trained for the range 1.5 to 3, okay, which is typically what you use. Okay. Now let's check. Okay. So now what I'll do is I'll take MOPS as my LE and change analyte to hydrochloric acid. Okay. So now LE is still faster than TE, but my analyte is faster than LE. So let's see. Okay. So it gives you this condition that it's very sure that it's not going to work. Okay. But you can actually simulate more complicated cases also over here, which might not be so trivial. Okay, this is a trivial example, but the benefit is that, you know, I found it useful because many times you are in middle of the experiment, you think, okay, let me use this. So then you don't want to set up simulations, you just open it on phone or computer, quickly see, okay, will this work? Okay, most likely it's going to work, so you can try it out. Okay. So for quick, like, initial screening of various electrolyte systems, this is very good because you don't have to set up detailed simulations. But if you really want to understand how, you know, simulation is progressing, how focusing and separation is progressing, then you actually really have to do the full simulation, okay, which is also not hard to do. Okay. Are you able to understand? I'll be available after the class also, so if there's any help required, I'll help you after the class. So yeah.
Now you've got all your databases. How far are you away where this says, no, this is not going to work, but maybe change your leading electrolytes to, well, not sure what you with chloride, but what you choose, change your leading electrolytes. But how big would a step be if you say, no, this is not going to work, but your leading electrolyte?
Yeah, yeah. So actually,
so suggested
yeah.
alternatives.
So let's see. So let's fix our LE over here. Okay, LE and background is fixed. Let's just try to play with TE and analyte. This is predicting the whole experiment, whether analyte mobility is between LE mobility and TE mobility. Okay. So now if we just run this, obviously it's having issues because I have given the same analyte here. But let's see. Let's get it to the working point, because okay, so it says MOPS is will get focused between heaps and hydrochloric acid. We are back to what we've seen earlier. Okay, now you can try to change the mobility value. Okay, so let's say that I'll just customize this. So I'll say pK 7.5. Okay, the only difference now is that the mobilities are different. So let's see if it predicts. Okay, so it's still predicting because analyte mobility is higher than the TE mobility. So we can start decreasing the TE mobility, the analyte mobility. Okay, so it is 25 and this is 23.5. So let's See, it is still predicting, but this red one is slightly increasing. It's getting a bit more confused. Okay, so we go to 24. Okay, this is slightly more confused. If we do 23, okay, so it's giving a wrong prediction, but this peak is also slightly bigger. Okay, because ideally now it's not able to recognize between 23 and 23.5. Okay, because it depends on the simulation data, whether that data was available in this range. Okay, so now there is some confusion. So the point is that once you start seeing confusion in the code, you have to verify with the exact simulator. So maybe in certain cases you saw, okay, there was prediction, but now 21 and 23.5 it is clearly able to differentiate. So as I said, this is not a accurate tool. Okay, this is a tool that if you have large number of choices, you can quickly screen, so that now you can do a better simulation. Yeah, but it's handy because you can get some estimate. Okay, if this green and red peaks are really big, you are more or less sure that it is going to work.
Ideally, there should not be any red.
Ideally, it should not be there.
It should not be there.
Yeah.
Complete successful experiment.
Yeah. I've deliberately done a bad experiment here. Okay. So this is just for ITP. I mean, it's not for general purpose use. So let's see. So I hope this is open for you now, for everyone. Chal gaya piche? For you? Okay. So now let's try to run this. Okay. So tell me, like, what do you want to simulate? If you have some choice, we can try to set up that. Okay. So what you have to do in this is that first you need to add all the species that are present. So let's just simulate the same. Let's just I think this is not limited to ITP. We can simulate whatever you want. Okay, but let's just simulate the ITP problem, that the buffer that we have already set up. Okay, so what I'll do is go to search. Okay, I'll just add all the species. So you do add hydrochloric acid, and you can add it to your model. Okay. So you search hydrochloric acid in the database and click add. Okay, let me show you for another one. Okay, in search, let's search HEPES, heaps, and then you hit add. Okay, are you able to do it, ma'am?
Yes.
Okay, then another one is, let's say, tris, TRIS. Okay, there's bistris and tris. I'll add tris. Okay, and then I will add MOPS, MOPS. Okay, so what you can do is, in the database, just search these 4 names and just add them to your model. Okay. Are you able to do it? Okay. Okay. So now what you can do is, actually, if you scroll down, you will see concentrations, but then we have not defined the we have not defined the profiles as yet. Okay. So what we'll do is, now we have to tell where is hydrochloric acid, where is heaps, where is tris. Okay. All we have just told the model is that these are the species that we have. So what I do is that hydrochloric acid we want to add on the right hand side of the the computational domain. So, I will say right plateau, okay, and I will define its concentration. So, let us say 100 millimolar. This is the injection length, okay. We can use 20. Okay. So, what do we need? Look at this. Okay. We need to define the concentration of the leading electrolyte, the initial concentration distribution of leading electrolyte. So, I have concentration versus x. I want some LE like this. So, I choose the option right plateau. So, it makes a profile like this, but you need to tell at what point it is injected. So, that is this x injection. You can just write 20 or 15, because I am simulating a domain of 40 millimeters length at 15 millimeter length from the left hand side. Okay. The LE zone has started, okay, initially, and its concentration is 100. So, you get initial profile something like this. Okay. It is 100 up till here, and then at 15 it is going to 0. Okay. So, I suggest that you can use these values here, 100 and 15. Is that okay? Are you able to do it? Okay. So, now what do we want? We want heaps as a TE, trailing electrolyte. So, we want a zone on the left hand side. So, we say left plateau. You can choose some value, you can take 10, let us say millimolar, and you inject it at, you can even inject it at 15. Okay. So, this is my LE, and this is my TE. Okay. Is that fine? On the back. Okay. So, let me, okay. Trace is my counter ion. I will just use uniform. I am taking it to be 200 millimolar, because I am taking it to be twice that of hydrochloric acid. So, this is my system. Actually, I can slightly increase the TE concentration, so that it is visible. So, maybe 30 I can do. Okay. So, this is my initial condition. Please have a look. So, this is hydrochloric acid on the right hand side. Okay. This is heaps on the left hand side, and trace is my background counter ion on the top. Are you able to get? Okay. So, now what we need to do is we need to add our analyte. Okay. So, analyte we will add as a peak at, let us see, okay. Okay. So, what I have done is, for peaks in this code you have to define as the location where the peak is initially, okay, what is the amount of sample that is injected in these units. So, just put 40, 15, and what is the width, injection width of the peak. Okay. So, what you will get is, this is the peak that you will get, this red colored peak over here of the sample, and this is the initial condition. Okay. Are you in the back, are you able to get up till this point? Okay, try to use these parameters. Okay, see if you have these parameters. It is just like a graphical way to define the initial conditions. That's all. Yeah.
Or we have divided the length of various.
Yeah. So that is, I'm just giving an example. In an actual simulation, actual experiment, you have to see from where you are starting your where in the channel these samples are injected. Okay. So think of this as a capillary which is 40 millimeters long, and imagine that, and initially you had LE up till here and TE up till here. Okay. Yeah, that's an initial condition. Okay. And the samples were initially placed in between LE and TE. That's what we are just imagining. Okay. So another thing that is that we need to choose how long the simulation has to run. This is the physical time. Like the experiment will run for 50 seconds, not on the computer, in reality. Okay, the number of grid points, you can just take 1000 grid points, and the current. Okay, current and the cross sectional area. So you just use default values, whatever these are, but make sure that the current is negative. Okay, so let me see if this runs on my computer. So yeah. So if I hit start, you see that the initial sample concentration, it is increasing. Okay. So you can predict the dynamics of ITP just on your computer. It's very user friendly way. You know, I did discuss the equations and all those things, but for an end user doesn't really need to know what is going into it, but you know that you know the equations, then you will know the limitations of the tool, right? Somebody will say I can simulate DNA and all these things, but the models for mobility are that we are just taking weak electrolytes. Okay, there's no gel and all those things involved. Okay, are you able to get this at the back? So now what we can do is we can we don't set up the simulation completely in one go, so we can just try to now complicate things. Okay, we can add more analytes. Okay, so let me add more analytes. So let's see. Okay, we can try adding something called mess. Okay, and then add it in a different amount at the same location, maybe different way. Okay, so now I have two analytes. Okay, as you see, they have different mobility and different pKa. Okay. Okay, so you will get an initial condition which looks something like this. Okay, so you can use these parameters. Okay, so now are you able to do it, ma'am? So if you now hit start, okay, what you see is a very complicated process, but initially the two analytes are mixed with each other. Okay, not only their concentration is increasing, their zones are also separating, and eventually you will see two purified zones. You should see. Okay, another thing that you see is that initial TE concentration was this. It has increased to this value. Okay, as I said, the TE concentration will adapt to a value which is proportional to the LE concentration. The analytes are slowly getting purified into two distinct zones. Okay. But what you see over here is that the red analyte, that is MOPS, is not in sufficient quantity to form a plateau. Okay, it still looks like a peak. So, what I suggest is you go back here and maybe increase the initial amount of MOPs. So, you can take 150, let us say. So that you have an initial condition which looks like this, and now if you run this code, okay, you should see two nice purified plateau zones. Now, while the simulation is running, okay, we can see that the code also predicts what is the local electric field and the pH of the solution. Okay. So, you know in brown color it is predicting what is the pH of the various. Okay, you don't want, see, you can't predict this pH in advance, okay, because it's a very dynamic process. Okay. So, now you see you have two zones, they are trying to separate, but separation is not complete. Okay, it is going to take some time. So, in an actual experiment we need to know how much time we should wait or how long the channel should be, so that the separation is complete. All of these things we can design using simulations. So, slowly you are seeing that we are going towards two purified zones, and you can also predict the pH. Okay. Okay, so now we see that the simulation is complete. Okay, the focusing is complete. Okay, you have attained steady focusing of these animals. Okay. Okay, and they also leave the domain if you let it go simulation for longer time. Is that okay? So, this is how you can set up ITP simulations, but in the same code you can simulate whatever you want. Okay, there is no limit to what you can do, because it is a general model, you can simulate whatever you want. Okay. So, what we can do is we can try to simulate, what should we simulate? Capillary zone electrophoresis is what we can try to simulate, and that simulation is easier. Okay. So, let us say we want to now separate these two analytes, the same analytes using zone electrophoresis, but now we do not need a TE. Okay. So, we can just get rid of this. Okay. We can get rid of heaps. I can use, I need a uniform concentration of hydrochloric acid to make the background electrolyte. So, my background electrolyte should look like this. It has 100 millimolar hydrochloric acid, 200 millimolar trace. Okay, I have deleted heaps. Okay. And maybe for larger length you can start injecting this at earlier, okay, at the inlet. Okay, so we are trying to just have a look here. Okay, we are trying to set up initial conditions like this, where we have uniform background electrolyte consisting of 200 millimolar trace, 100 millimolar hydrochloric acid, and I have two analytes which are initially mixed. So, these are overlapping peaks at x equals to 5. So, this initial condition is what we are trying to use. Okay, so, just try to use these values. Okay. So, HCl and trace are uniform, others are peaks injected at x equals to 5, and for our calculations we can just use these values. Okay. Are you able to set up? So, if you do it correctly, you should get this. Okay. Okay. So, in this case, actually you see the initial analyte concentration is pretty high. So, you might see significant electromigration dispersion. Okay. So, what's gone wrong? Oh, sorry. So, oh, let's see.
We have to reduce it even?
No, no. Actually, this code can actually run for this. Let me run it. Actually, the graphical interface is made for is tuned for ITP. It is giving just some bug, okay, over here, but concentration gaps are present. Please bring injections closer. Let me set up. I have a input file which can probably fix it. Let's see. Think there is some bug. Okay, let's see. Let me try. Hmm? Same data. Yeah, because I know the code is, I mean, the graphical interface is just checking if the initial condition is consistent with ITP, but actually you can run it for zone electrophoresis also. So, that is what I am trying. Okay. Otherwise, so So manually it's not allowing me. Let me see. Yeah. Okay, I think maybe there's been change to some of this code afterwards. Okay, but let me show you something else actually. I think there is some limitation to what initial condition it is allowing, but actually I can show you with other tools that we have. So let's see. Okay, but that you might not be able. You can download it, but if you search, but spice. Okay, so let's. I'll just show you another simulator. Okay, so this you can use. Okay, I'm not going to teach you this how to use this, but it's on my website. You can learn it. So for zone electrophoresis, okay, the same simulation we are just trying to show you. So okay, this one is very fast. Okay, because it's not on browser. So we had initially 2 zones. Okay, which were overlapping, and they have separated into distinct zones. Okay, so this is the spice code that I'm using. So it's pretty fast in that way. Okay, and this can also do ITP. Okay, this is for the 4 analytes ITP separation. So you can see. Okay, this code is much more accurate, but it's a bit difficult to use. Okay, for beginners. But I had an input file for zone electrophoresis. I wanted to see if it could work, but somehow I'm having difficulties in uploading it.
Right now it is only working for ITP.
Yeah, there is a way to make it work for others also, but I'm trying to do it. Actually, I had saved input files, but maybe the version of this code has changed, and now it is not taking that. Yeah, there is some change to this code. I'm sorry, so it's not allowing us. Let's see if it loads. Maybe we can work. Okay, so we can try this. And now let me add. Let me just try with
The
this.
voice I've tried it before.
Yeah, this works, right? I mean, it's not the best way to do it, but it works. Okay, so let me just show you. Okay, so actually there are multiple profiles over here. Okay, but what I have done is that I have added hydrochloric acid on the right hand side, hydrochloric acid on the left hand side, trace on the right hand side, trace on the left hand side, and the samples in between. Okay, so this is the initial condition I have, but this red and blue are actually the same species. Just because I have added them separately, it looks like this. But now, if we try to run the simulation, okay, you can try looking at these two peaks over here. Okay, so they are going to separate over time and also get distorted over time. Okay, so there is like severe electromigration dispersion over here. Okay, and if instead we have low concentrations, okay, then this electromigration dispersion will not be there. Okay, so let's see. So I can zoom in. Okay, so now these two peaks are getting separated. Now the simulation ran for 500 seconds. Okay, so I've just zoomed in and run the simulation for longer time. So these were the two peaks initially that were overlapping, and now they are separating into distinct zones. Okay, so now the point to note over here is that while these zones are moving, let's track the electric field. Okay, so what you see over here is that these zones are actually affecting the local electric field also, and that is the reason this zone dispersion is taking place. If the zone concentrations were low, that the electric field is not modified, you will not get this dispersion. So what we can do is we can further try to reduce. So we have 10, and let's say we take width of 1. Maybe also reduce this. Okay, so now the dispersion has significantly reduced, if not like completely eliminated. But typically what we do is that we have very low concentrations for the samples. So, you will need to have like 1:100 ratio of the concentrations, and then you will see that the electromigration dispersion is not significant. But now you can see the peaks are not so distorted as we had
200 for some analyte
background.
and
Essentially, this presence of analyte should not modify the electric field significantly. If it affects, then that means that your you will get nonlinear effects. For example, if I do here 50 and 50 and I start the simulation, okay. So, now you see that one side has sharpened a lot and there is significant zone dispersion. Okay. So, that is what we need to avoid. Okay. So, I think I have just given you one quick lecture on how we can use these tools for simulation. Okay. You can try out the other tools as well. Let us see where it is. Okay, all of these tools are available on internet. Okay. So, you can download them, you can read the help, and you can try to run these codes as well. Okay.
The help documentation of all of them is really extensive.
Yeah, there's a lot of
lectures. I just give the students the manuals and tell them, come solve this problem by tomorrow, and they can all do it.
yeah, it's very easy, and the video, some of them have video tutorials also. Okay. Okay, so we can stop this lecture here. Okay, we have one more lecture.
I'm happy to do the microfabrication for you. I've full day of microfabrication anyway.
Okay, so if we can skip, is it okay?
Not today. Today and next month.
No, let's see.
Hello. Today and next month.
The schedule said there was another one on microfabrication, but I'm covering so much microfabrication.
Yeah, so maybe you can cover that, right? Yeah. So I don't know how. Let's see. Recent.
So you are returning to Delhi today?
No, I'm going to Chandigarh.
Because I talk about the whole range of microfabrication.
Yeah, then I think it's overlapping. So there was this 3 to 4 for device fabrication, but if it's possible, then we can skip.
Professor Malik is in charge.
Hello. 1 minute 5 3 4 5 6. 5 3 4 5 6. दोबारा लॉगिन कर दो.
लॉगिन तो
हाँ जी.
मुझे वो नहीं पता ना.
5 3 4 5 6.
I think that's your package.
That's my boss.
बस.
That's the show and tell for Monday.
Need to ask him. He's busy somewhere else.
Are we okay to conclude today?
Yes.
Because the timetable said we had another one on microfabrication, but I
No,
can
no,
easily
no.
cover that on Monday.
Yes.
Okay,
We're good to go.
good. So, yeah, I also got some microfluidic devices after the lecture. If you want to see, we can have a look. But yeah, so any questions? Maybe we can.
Please go and have a look at the devices because I think you will have glass.
We have glass, PDMS, PMMA, everything.
I've got some 3D printed and PDMS ones and COC ones coming in and no glass. So
Yeah. So maybe I can share. Let's see. These are standard off-the-shelf devices. This is made in glass. I don't know how this broke, but this is just 3D printed. I mean, this is not a big device. Okay. So,
It's gonna work now.
what else? Let's see. Which one was broken? This is broken, but this is I mean, it's not the complete device, but you can see this mesh.
Yeah.
This is made with our printer.
the 3D printer.
3D printer is this one is 3D printed. Yeah, so that fine resolution we can
Yeah.
print on silicon wafer.
So there are polymer threads and
Yeah.
then the cavity between.
No.
So you print the lines and then cast PDMS
Yeah,
over
yeah,
it and
yeah,
then
yeah.
becomes channels.
Yeah.
How it's done?
So
Electrospinning.
it's a printing technology.
Okay.
So we print some features, and then we pour a polymer, peel it off, and then we bond it on glass. Okay. Then what else I have? This is probably for some other process. These are machined, directly machined by CNC. So a glass, you can have a look here.
This one you gave me for glass.
Yeah, this is glass. You can have a look. This is glass. Actually, if you look,
It becomes a lot more real if you
Look.
put it in your hands.
Yeah.
if you look in the light,
So
okay, you will see a cross connecting from this reservoir to this to this.